If HA is a generic acid and donates this proton, the electrons in this bond, so the electrons in magenta, are left behind on A to form A-. So A- is the conjugate base to HA. If A- is stable, then HA is more likely to donate this proton. Therefore, if you want to determine the acidity of a compound, you can look at the stability of the conjugate base. The more stable the conjugate base, the more likely the acid is to donate a proton. Therefore, the more stable the conjugate base, the stronger the acid. Let's use that concept and let's look at these four compounds down here. So we'll start with methane. The pKa for this proton on methane is approximately 48. For ammonia, the pKa for this proton is about 36, and if we look at water, the pKa for this proton is about 16. And finally, for HF, this proton has a pKa of about 3. We know that the lower the pKa value, the stronger the acid. So as we move to the right, we see a decrease in pKa values from 48 to 36 to 16 to 3. Therefore, as we go to the right, we see an increase in acid strength. We see an increase in acid strength. So HF is the strongest acid out of these four. And if HF is the strongest acid out of these four, then HF must have the most stable conjugate base. So now let's think about the conjugate bases for all four of these compounds. So let me go down here and we'll get some more room. If we take this proton from methane, then these electrons are left behind on the carbon. So the carbon gets a -1 formal charge. For ammonia, if we took this proton, then these electrons are left on the nitrogen. So the nitrogen has a -1 formal charge. For water, if we took this proton, these electrons are left on the oxygen to form the hydroxide anion as our conjugate base, with a -1 formal charge on the oxygen. And finally, if we took this proton, then these electrons would be left behind on the fluorine to form the fluoride anion. We already know that HF is the strongest acid out of these four, and the strongest acid must have the most stable conjugate base. So the fluoride anion must be the most stable conjugate base. So as we move to the right, we're increasing in the stability. We're increasing in the stability of the conjugate base. And we can explain that trend by looking at the element that has the negative charge. Right? This has a negative charge on carbon, and this was our least stable conjugate base. Then we go to nitrogen with a negative charge. We get a little bit more stable. We go to oxygen with a -1 charge. We get a little bit more stable. And finally, we get to fluorine with a negative charge, and we have the most stable conjugate base. That's the same trend as electronegativity. So if you look at carbon, nitrogen, oxygen, and fluorine, as you move to the right on the periodic table, you know you increase in electronegativity, with fluorine being the most electronegative element. And the most electronegative element attracts electrons the most. It likes to have electrons around it, and therefore it makes sense that fluorine is the best at stabilizing a negative charge. And that makes this the most stable conjugate base. And if this is the most stable conjugate base, the fluoride anion is the most stable conjugate base, that means that HF must be the strongest acid. So when you're thinking about acid strength, think about the stabilization of the conjugate base and the different factors that can do that. Electronegativity is one of those factors to think about.